This video is going to help you kind of understand what you did in lab number 1. So this was the water and temperature lab that we did. So we're going to kind of focus on the data that you collected and how to graph that data. So page number 5 is the first area here where we start to see some data. Now remember, you went through kind of a data analysis phase on the LabQuest unit. So you had the screen of the LabQuest. And you collected data. So you should have had a graph on the LabQuest that had 2 different lines, and they probably looked something kind of like this. So one line probably looked a little bit steeper, and the other one was a little bit less steep or kind of more leveled off. So from there, remember that you took the slope of the line, and the slope of the line is just how much this line, basically how steep it is, all right? So this is the slope, and this is that M value that you got when you did the analysis steps kind of up here and on the previous page. All right, so those are the numbers that you should have put in to this area right here. All right, so quick note, so the data that you collected on the LabQuest unit, this is what we call the raw data. All right, and the raw data is not what we are graphing down here. Okay, so we don't want the raw data. What we did is we did some analysis, and we ended up making some analyzed data. All right, so we looked at that slope, and we looked at this rate and temperature change over time. So this is the data in this table right here that is going to go on this graph down here. All right, so you should have gotten some temperatures, the initial temps for the room temperature water and the hot water. So I'm just going to make up some numbers because I don't have actual data in front of me. But let's say your room temperature water started out at, we'll say 25 degrees. And it's really important that you put units here, because if I just write 25, I don't know if that means 25 degrees Celsius or 25 degrees Fahrenheit, or I could be talking about 25 cupcakes. So without units, that number is really meaningless. So I'm going to put in degrees Celsius. For the hot water bath, let's just say it was maybe around 50. Now your numbers are going to be different because you have actual data that you actually measured, but it should be somewhere, kind of around those numbers. Now for the rate of the temperature change, remember that this right here is that M value that you got from the LabQuest unit. So you should end up with numbers that are negative, and they're probably you might have let's say a negative 0.02, or you might have like a negative 1 or 2 or something like that. So obviously your numbers are going to be different from mine, but they should look something kind of like that. So if you've got a positive number, or if you have a number that is not a, less than or smaller than 1, then you've got the wrong number. All right, so it should be a negative 0 point something. All right, now as I mentioned over here, this is the data that we are going to be putting on this graph down here. So a few things to point out. So our initial water temperature right here, this is our independent variable, and it goes on our x-axis. All right, so our x-axis is our horizontal axis here. All right, so we're going to first of all put a label because we need to know what this axis means. So we're going to write initial water temperature. And we're going to put the unit in parentheses. So parentheses degrees Celsius. All right. The rate of temperature change, oops, sorry, touched the wrong thing there. So the rate of temperature change over here, which I'm going to do in green, this is our dependent variable, and it's going to go on the y-axis. All right, so we're going to have our y-axis. So our y-axis, by the way, is the vertical axis over here. All right, so we're going to do rate of temperature change. And once again, we want to make sure that we include those units, because without units, it doesn't mean anything. And typically you would put it after the title. I'm kind of running out of room, so I'm going to write it above just so you can see exactly what the units are. And to make it a little bit easier, let's go ahead and make the units negative. All right, so let's say negative degrees Celsius per second. All right, now by making this negative right here, we can now kind of treat these almost like a positive, because we've basically taken this and put it into the units. All right, so that's going to help us when we actually make our scale for that side there. So now that we've got our dependent variable and our independent variable and our dependent variables labeled, we need to make up our axes. And one really important thing with our axis is that we need to keep the scales consistent. So let's look at our initial water temperature first. All right, so we don't want to say that this square is worth 2 degrees and the next one's worth, maybe like 3 degrees. The next one. So if you see what I'm doing right here, this is not a consistent scale, all right? Because this box right here is equal to 2. This box is equal to 3. This one's equal to 5. And this one's equal to 10. And that is bad, all right? So it's not consistent. We need to make sure that every box is equal to the same value. So let me erase that and let's go. So we need to be able to get up to 50. So let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Not enough there. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Okay, so we'll go up by 5s. Oops. All right, so 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. Now you want your scale to fill up as much of the graph as possible, because you don't want to make a teeny tiny little graph, because then it's hard to read it and see what you're looking at. So with my current scale here, every single box on the x-axis is worth 5 degrees Celsius. All right. For the dependent variable, I need to be able to get from 0.02 to 0.13, or I can kind of just see this as going from 2 to 13. All right, so in this case, I think I can go up by 0.1. So I can go 0.1, 2, 3, 4, 5, 6, 7, 8. Oh, and you know what? I just caught that I made a mistake here, because these are supposed to be 0.01 and 0.02. So let me actually fix that. Sorry about that. All right, so 0.01, 0.02, 0.03, 0.04, 0.05, so 6, 7, 8, 9. So that one's going to make this one up here 0.1. I kind of skipped over these just because by labeling everyone, it's kind of crowded. You can also do that, but it helps to kind of keep it consistent. So you might want to, for example, just label every other one. So all right. So notice how each box here is equal to 0.1. All right, so this box is equal to 0.1, this one is equal to 0.1, this one is equal to 0.1. So let me erase that. All right, so now it's time to graph your data. Now, the big question here is, are you going to do a line graph or a bar graph? The easiest way to determine this is by looking at your independent variable. If your independent variable has numbers, so we have numbers down here, right? We have our degrees Celsius. We have numbers here. We're going to do a line graph. All right. Now, so when we do a bar graph, how is that different? So a bar graph would be if we were doing just kind of like categories. So hot versus cold water. If we were doing something like that, then we would do a bar graph. And that's because we do not have numbers down here on the x-axis. But for this particular set of data, we have numbers. So we are going to do a line graph. All right. So to actually graph the data, you need to match up these 2 points. So for our room temperature data, we're going to match up 25 degrees, which is this kind of line right here. And we're going to match it up with 0.02, which is this line here. So our first data point is going to be right there. All right, so that is just graphing this information and this information and seeing where they cross on the graph. All right, to graph the hot water one, we're going to do the same thing, but now we have to come over to 50 and go up to 13, like that. And then to finish our graph, we are just going to connect the dots. All right. So there's one thing that we're still missing on this graph here, and that thing that's missing is the title. So we need to put a title, so that's this descriptive title, up at the top so that somebody looking at this graph can easily tell what they're about to learn. One easy way of writing a title that is descriptive is to follow the formula of writing the effect of the independent variable on the dependent variable. So for this particular graph, the title would be the effect of the, and we would fill the independent variable in with what it says up here. So the effect of the initial water temperature on the dependent variable. And here, remember, our dependent variable is what we've been doing in green. So we would fill this in with the rate of temperature change. All right, so we would kind of get rid of that and just fill in with the actual title. So the title would be the effect of the initial water temperature on the rate of temperature change. All right, so you can see by kind of following the colors that I used here, you can see that all of this information is connected, right? So you can see that the independent variable here gets graphed down here. We're doing a line graph because this has numbers. You can see that this information also gets put in the title up here. For the dependent variable, you can see that it's here in our data table, and we put it on our y-axis here, and it's also reflected in the title here. For part 2 of the experiment, we're testing a different independent variable. So the dependent variable is going to stay the same, but the independent variable is going to be comparing the rate of temperature change between water and ethanol. So water and ethanol are our independent variable. Now, as part of this process, you need to develop a hypothesis and a prediction, but sometimes it's easier to start by identifying the independent and dependent variables down here, and then working backwards to come up with the hypothesis and prediction. So we already identified the independent variables. So we're basically testing water versus ethanol. You could also just write this as, if you wanted to just say like the substance, or we'll say type of substance. All right, so that's what we're testing for our independent variable. Now for our dependent variable, we're testing, or we're measuring and recording the same thing we did in activity 1. So we're going to be looking at the rate of temperature change between these two liquids. All right, so from there, now we can work backwards and kind of figure out what our hypothesis is. So typically, you can kind of follow almost like a little bit of a formula in order to develop a hypothesis. And this formula isn't going to work for every experiment that you do, but it works for this case, and it'll work in a lot of cases. And that formula is just to write that the independent variable either will or will not affect the dependent variable. All right, so to apply that to today's lab in this, this second activity here, we would say the substance type. All right, so remember our water versus alcohol. And then we need to decide, do we think it is going to affect the dependent variable or is it not? So you can pick either one. I'm just going to go with the will option. So we'll say the substance type will affect the rate of temperature change. All right, so I just filled in for the dependent variable and the independent variable. And then I chose that I think that the rate of temperature change is going to be different for these two substances that we're testing. Now, it's totally valid to go with the other option. It's totally valid to say that you don't think that there's going to be a difference. So you could say the substance type will not affect the rate of temperature change. So both of those are correct. A hypothesis is just kind of a statement that you're trying to either collect data to support it or not support it. So either one is a valid hypothesis. So from there, we can now kind of jump from the hypothesis down to the prediction. And we're still going to stick with kind of focusing on our independent variable and our dependent variable. The prediction is just going to be more of a kind of a more specific, so more specific as in how will it affect it? All right, so how will the independent variable affect the dependent variable? All right, and once again, there's kind of a formula that doesn't work for every instance, but it'll work here, where we can kind of say if the independent variable, then something's going to happen to the dependent variable. Now, we might have to play around with the wording a little bit, but we can say if we test water and ethanol, all right, so this is the if we test this independent variable, then the rates of temperature change will be different. All right, so once again, this is kind of tying back to that we think that they will be different. Now, if you chose the will not option, then your prediction is going to look a little different. And you could say, if we test water and ethanol, then the rates of temperature change will not be different. So you would just kind of add a not in there. You can even take this a step further and make an even more specific prediction. So maybe you think that water is going to change temperature faster than ethanol. Then you can say the rate of temperature change. So you can basically keep this, but then move on to say, so the rate of temperature change will be faster for water than ethanol. Or if you think the opposite, then you can switch the position of water and ethanol. So these are all valid predictions. So the part that says, they will or will not be different, that's actually pretty generic. It's kind of better if you add a little bit more specific into your prediction, because your prediction is more of like what you think is actually going to happen. Now, if we look at the data table and the graph for part 2, you can apply a lot of what you learned in part 1 to making the graph for part 2. So first of all, our substance is going to be our independent variable. And our rate of temperature change is going to be our dependent variable. All right, so you should have a number in here that is kind of similar to what you had in the first part, where you're going to have a negative 0 point and then some number. So I'm just going to make up numbers once again. Actually, I'll just use the same numbers I used in the first part, just because. All right. So this is the data that you are graphing. All right. So this is the data that's going to go on the graph down here. And you got this data here. This was that M value that you got from the LabQuest unit. All right, so just like we talked about with the first graph, you're going to put the independent variable on the x-axis down here. And you're going to put your dependent variable on the y-axis up here. And remember, you want to include the units. So when you're labeling, for example, your y-axis, you would put rate of temperature change. And we'll do the same thing we did with the first part, where we're going to add a negative sign before the units. So we're going to say negative degrees Celsius per second. that means that we can kind of ignore this negative sign here when we're graphing it and just graph it as if it's a positive. Now, one key difference here. So remember, we talked about when do you do a line graph and when do you do a bar graph. You can only do a line graph if the independent variable has numbers. In this case, sure, it says 70% ethanol right there, but let's ignore that because we don't have a number for water, right? We're not talking about a percentage or a concentration. We're just talking about we have water and we have ethanol. So we don't really have numbers that we can put down here on our x-axis. So that means that for this data set, we have to do a bar graph because we can't do a line graph. So you're going to have one area that's going to be for water and another area for ethanol. Now, one key thing is you'll notice that I made the widths of these bars the same. So each one is equal to 3 squares wide. That's because we want to make everything look consistent, because if you have one bar that is fatter than the other, then it skews the visual nature of the data, and it makes it not as easy to interpret and analyze. So I kept those the same. All right, so in this case, for the dependent variable, once again, we want to keep the scale on the y-axis consistent. So we went up by 0.1. So I'm actually going to go up by 0.2 on this one. I'm going to go up by 0.01, but I'm only going to label it every other one. So 0.02, 0.04, 0.06, 0.08, 0.1, 0.12, and 0.14. Sorry, hopefully yours is going to look neater than mine. So to do our graphing, so if water was 0.02, then we would make our bar go up to the 0.02 line. If ethanol is 13, then we're going to take it all the way up to the 13 line right here. All right, and you can you can color it in if you want. You can use different colors. It doesn't really matter as long as you're kind of staying consistent so that it looks kind of easy to compare these two. Now remember, this is not the real data, so don't make a graph like this. You need to make sure that your graph reflects what your data says kind of up here. All right. And also go back and review the part about the first graph to put your title. All right. So remember the title, you're going to say the effect of the independent variable on the dependent variable, but you're going to actually plug in what the independent variable and dependent variables are. So I will let you do that part on your own, and that will show you that graph there.